Now we have another characterization in terms of open set. So very interesting characterization which says that a function f from a metric space x to another metric space y is continuous on x if and only if inverse image of open set in x is open. So the inverse image of open set in y is open in x. Okay. So here is f is continuous on x if and only if f inverse g is open in x whenever g is open in y. Let's prove. Very simple. Assume that f is continuous on x. Okay. So we are assuming that f is continuous on x. Then we will have to prove that f inverse g is open in x whenever g is open in y. And so let us take g is any open set in y. Okay, then we will have to prove that the inverse image of g under f is open in x. Okay, if f inverse g is empty set, so we know that the empty set is open, so nothing. So there is nothing to prove. So we assume that the f inverse g is non-empty. So if it is non-empty, so there should be some element in this set. So let us take x lies in f inverse g, and therefore f of x is in g. Now since g is open and f of x element in g, it means that f of x is the center of some open sphere contained in this g. So there exists an open sphere as epsilon f of x contained in g for some epsilon is positive. Now by the definition of the continuity, okay, for some epsilon, for every epsilon positive there exists a delta. So corresponding to this epsilon there exists a delta positive such that the image of the open sphere with center at x radius delta must be a subset of the open sphere f of x, open sphere with center at f of x and radius epsilon. Okay, and since f of epsilon x, this is a subset of g, this means that this is a subset of g. So this is a subset of g. It means that as delta x is a subset of f inverse g. So f inverse g. So it means that what we have done, we have taken an element x in f inverse g and we have proved that this is the center of some open sphere contained in this set. It means that so since x was arbitrary, so every element of this set is the center of some open sphere contained in it, and therefore f inverse g is open. So now you can see here is this is the space x, this is a space your y. So here is we have this, here you have g is your open set, and here then the inverse image of g is this one, suppose f inverse g. Okay, so for every open sphere, so if this is, we have to prove that this is open. So to prove that this is open, you take a point x with center x. Okay, then this is the center of some open sphere. So this is your, we have to prove that so let's take the converse part. Assume that g in f inverse g is open in x whenever g is open in y. Okay, then we will prove, we have to prove that f is continuous. So let x be arbitrary and epsilon be given. Okay, so let us take x is arbitrary whose image is f of x. Okay, and this is epsilon is given. Then of course the image of x is in f of x. And the open sphere, this open sphere is the open sphere with center f of x naught and radius epsilon. Okay, and the open sphere is an open set. Okay, and therefore the open sphere is an open set. Therefore, by the assumption that inverse image of open set is open, so inverse image of this would be what? Would be the F inverse S epsilon f of x is open in X, and therefore X lies in F inverse. So you take in this set, and consequently you can see that there exists delta is greater than 0, such that because this is your okay, so this is your open and X is in this set. So this set is an interior point of this set. So this is the center of some open sphere contained in this. So as delta X is a subset of this one. And now take the F both the side, then F of as delta X is a subset of this one. And hence F is continuous at X. Since X was arbitrary, F is continuous on capital X. That is, F is continuous at every point of X. So that was the characterization in terms of an open characterization of a continuous function in terms of an open set. Okay, now since we have already proved that the complement of an open set is a closed set. So this characterization can be seen as a function f from a metric space X to another metric space Y is continuous on X if and only if the inverse image of closed set in Y is closed in X. So F inverse F is closed in X whenever F is closed in Y. So this can be proved in view of the previous result. This can be proved by using the ordinary set theory and the fact that the complement of open set is closed. So let f be a continuous function and capital F be a closed subset in Y. Okay, be a closed subset in Y, then we will have to prove that the F inverse capital F is closed. Okay, in other words, the complement of this is open in X. So now Y F is closed in Y, and therefore the complement of F in Y is open in Y, and we have already proved that F is continuous. So inverse image of open set is open. So F inverse Y complement of F in Y is open in X. Okay, and now since F inverse capital F is equal to the complement of F inverse complement F inverse of complement of F, and the inverse of complement of F of Y, this is your open set. So this means that F inverse F is your closed set. So this is your closed set. This is we wanted to prove. Now converse, assume that F inverse F is closed in X whenever F is closed in Y. Then we have to show that F is continuous. To prove that F is continuous, again we will prove that the inverse image of open set is open. So let G be an open set in Y, then the complement of G in Y is closed in Y, and by the hypothesis F inverse the complement of G is closed in Y, and since F inverse G is equal to the complement of F inverse complement of G, and this set is closed and therefore this set is open. So this and hence this is your open, and hence F is continuous on X. So this can be proved very easily. So we have the characterization that the inverse image of closed set is closed, inverse image of open set is open, and then the function is continuous. So we can see that the inverse image of open set is open. Okay, the function is continuous if and only if inverse image of open set is open, but not the image of open set is open. Okay, similarly the inverse the function f is continuous if and only if the inverse image of closed set is closed, but not but we cannot say that the function f is continuous if and only if the image of closed set is closed. So here is we have the remark we say that if f is a continuous function from a metric space x to another metric space y, then the image f of g of an open set g in x may not be open in y. Okay, and the image f of a closed set in f in x need not be closed in y. Okay, so we can consider a function f from R to R defined as f of x is equal to x square. Then of course this function is continuous. Now consider the g is equal to open set -1 to 1, okay, in R, and we will see that f of g is equal to the closed interval 0, open interval 1, and this set is not open in R. So if the function is continuous, then the image of open set need not be open. Similarly, consider a function f from closed interval 1 to infinity to R defined by f of x is equal to 1 over x. Then again this function is continuous. Let us take a is equal to the whole space, okay, and then as a whole space a is your closed set, but as a whole space a is closed, but f of a is equal to the open interval 0, closed 1, and this is not closed in R, this is not closed here. So if the function is continuous, then the image of a closed set may not be closed. Now we have another characterization of a continuous function in terms of the closure. But before that, we can see that the function is continuous, then the image of closed set may not be closed. But we can say that a function f from a metric space x to another metric space y is continuous if and only if the image of closure of A is a subset of the closure of f of A for every subset A of x. So you can see that if a closure of A is a closed set, so f of the closure of A is a subset of closure of f of A. In case this means your closed set. So this f, the image of closure of A is a subset of the closure of image of f of A for every subset A of x. Now what will happen if A is closed? So if A is closed, then f of A closure is equal to f of A. So f of A is a subset of closure of f of A. But this may not be closed, as we have seen. This may not be closed. So this f of A must be a subset of closure of f of A, if A is your closed set. Now, prove this statement or prove this theorem. So let f be a continuous function. Okay, then we will prove that this inclusion holds good. So for that, if f is continuous function and f of a closure, because the closure of any set is a closed set, so, and f is continuous function, so the inverse image of closure of f of A is closed, okay, because the f of a closure is a closed set. Now we have f of A is a subset of f of a closure. We know that for any subset A is a subset of closure of A. So because this is a closure, so you operate the f inverse both the side, then we will see that the A is a subset of f inverse closure of f of A. Now we can take the closure both the sides, so closure of A is equal to the closure of this term. So closure of A is equal to this term. And now it means what? It means f inverse closure of f of A closure. So this is your closed set. So this set is your closed set. So this must be equal to F inverse F of A closure. So closure of A must be a subset of this one, because this is your closed set. And now operate F both the side, then we will see that F closure of A is a subset of closure of F of A. Now to prove the converse part, so this is holds good. Now to prove the converse parts, let us take F of closure of A is a subset of closure of F of A for every subset A of X. Then we will prove that F is continuous. So F is continuous. To prove that F is continuous, we will prove that the inverse image of closed set is closed. So let F be any closed set in Y. Then the closure of F is equal to F. Now we have the F of closure of F inverse F. Okay, this is a subset of F inverse closure of F inverse F. But this is what? This is equal to F. So this is equal to F, and we have the closure here, so we have the closure. But because F is closed, so this is equal to your F. And then we operate F inverse both the side, and we will see that this is a subset of F inverse F bar. But F inverse F is always subset of this one, closure of F inverse F. So therefore, the inverse of the closure of F inverse F is equal to F inverse F. Hence, F inverse F is a closed set in X, and therefore F is continuous on X. Now, we can summarize all these characterizations in the following theorem. We say that if X and Y be metric spaces and F is a function from X to Y, then the following statements are equivalent. That is to say, F is continuous on X if and only if for every sequence Xn converging to X implies F of Xn converges to F of X. If and only if the inverse image of open set is open, if and only if the inverse image of closed set is closed, if and only if the image of closure of A is a subset of the closure of F of A for all subset A of X. So these are the characterizations of a continuous functions in terms of sequence, in terms of closed set, in terms of open set, in terms of open set. Now, what can you say? Can you think that if I take, instead of taking the closure, if I consider the interior here and interior here. So F of interior of A is a subset of F of interior of F of A. Would it be equivalent to the continuity of the function? Okay, so this we will see later in the exercise. Now here is we have, as you have seen in the real analysis, the composition of continuous function is continuous. So also in case of metric spaces, the composition of continuous function is continuous. So that is to say, if X, Y, Z are metric spaces and F is a function from X to Y and G is a function from Y to Z are continuous, then the composition function G composition F from X to Z is continuous on X. And it can be proved very easily. So you can take any open set here, okay, and prove that the inverse image of open set under the this composition is open in X. So let G be an open set in Z. Then by continuity of G inverse capital G is open in Y. And then by continuity of F inverse G inverse capital G is open in X. And therefore, the composition of F inverse composition G inverse G is equal to G composition F whole inverse G is open in X, and therefore G composition F is open. So this is very simple one. Similarly, you can see that very easily that if the sum of two continuous functions is continuous, which is defined as that if f and g are continuous functions, then f plus g is defined as f of so you can define we can define the composition function like this. The f plus g x is equal to f of x plus g of x. The scalar product you can define f of x as alpha times f of x, and the product of two functions can be defined in this way, that f of x into g of x. So, if the function f and g are continuous, then the f plus g is continuous, alpha f is continuous for any alpha is real numbers, f and g is continuous. Okay, so this is given in this exercise, and as I mentioned that what will happen if I consider here is f of a interior of a is a subset of interior of f of a. Can we say that then the function is continuous? So here I have this question in the for this exercise. So let f be a function, continuous function from a metric space x to another metric space y. And now give an example to show that this does not hold. If f is continuous, then this does not. If f is continuous, then f of interior of a may not be a subset of interior of f of a for every subset a of x.